In 2017, NASA's Juno spacecraft was sailing past Uranus when it spotted something strange. It was an aurora. Not like the shimmering lights that dance across Earth's night sky, though this one was green and smelled like a rotten egg. It was also floating in midair, about 58 degrees north of Uranus's equator. That's a heck of a lot higher than Earth's auroras, which hug the planet's magnetic poles. What the heck is going on up there? What's happening to cause these mysterious auroras? And could they be a sign of even stranger things happening below the clouds? Let's get to the bottom of this twisted aurora mystery. Earth's auroras are pretty predictable. When charged particles from the sun, aka solar winds, slam into our upper atmosphere, they excite atoms in the gases. As the atoms return to their normal state, they release energy in the form of light. On Earth, we see these as beautiful curtains of shimmering green, red and blue light rippling back and forth around the magnetic poles. But if you swap out the word Earth for Uranus, the picture gets a bit more complicated. Like Earth, Uranus has a magnetic field that extends thousands of miles into space. But unlike Earth's magnetic field, which is pretty similar to a giant bar magnet, Uranus's magnetic field is a jumbled mess. Its magnetic poles aren't at its geographic poles, which are the top and bottom of the planet. Instead, Uranus's magnetic poles are tilted almost 60 degrees off of its rotational axis. Plus, the planet's magnetic field lines are twisted into an oval shape that bulges out way past the planet's surface. This means solar winds interact with Uranus in some seriously weird ways. Just like on Earth, most of the auroral activity happens at high latitudes, near the planet's magnetic poles. But unlike on Earth, Uranus's auroras are scattered all over the place. They appear far from the planet's magnetic poles and deep within its twisted magnetic field. They can also look totally different from our northern lights, taking on blotchy shapes that are smooth and featureless. They might stretch for thousands of kilometers without a ripple. Or they might flare up and down in a bumpy, bubbly pattern. And they can last anywhere from hours to days without stopping. Scientists think that these auroras are caused by the same thing, solar winds. But because Uranus's magnetic field is so weird, those solar winds must be interacting with the planet in a way that we don't fully understand yet. To figure out what's going on, let's start with what we do know. Solar winds are streams of charged particles blowing away from the sun at over 180 kilometers per second. That's over 640,000 kilometers per hour. Most of them are protons and electrons, stripped from the sun's outer atmosphere. Together, they make up a giant bubble of charged particles, known as the heliosphere, which surrounds our solar system and acts as a sort of protective shield between the planets and the even more energetic particles from interstellar space. But the heliosphere isn't a solid barrier. Solar winds can punch right through it and reach the planets. Some particles travel along the sun's rays, while others follow magnetic field lines all the way around the heliosphere. These space rogues get funneled toward the planet's magnetic fields, where they can be redirected toward their surfaces. And that's where auroras happen. Charged particles from the sun crash into a planet's atmosphere and excite atoms in the gases. As the atoms return to their normal state, they release energy in the form of light. On Earth, auroras form at high latitudes because our planet's magnetic field lines are concentrated around the poles. But on Uranus, the story is a little different. Its magnetic field lines are tilted and twisted in ways that we don't fully understand, which means that solar winds can hit Uranus at all kinds of weird angles. And instead of forming at the planet's magnetic poles, Uranus's auroras appear at middle latitudes, thousands of kilometers from the magnetic poles. They also last much longer than Earth's auroras, which are usually only visible for a few minutes or hours. That's because the twisted magnetic field lines near Uranus's equator act like a giant funnel, focusing the solar winds and channeling them onto the planet's surface. But if we know what causes auroras, and we know what Uranus's magnetic field looks like, why do we still have no idea how these auroras formed? Well, because scientists haven't been able to observe Uranus up close. We don't know exactly what its atmosphere is made of. All we have to go on are the clues from afar, and the data we've collected paints a confusing picture. Back in the 1970s, for example, Voyager 2 passed Uranus and detected water vapor in its atmosphere. But in the 2000s, the European Space Agency's Herschel Space Observatory found methane, not water vapor. Today, scientists think that both could be right. Uranus's atmosphere probably has both water ice clouds and methane, just like Earth. But unlike Earth, the boundary between them is really high up. The lowest clouds on Uranus are about 30 times higher above the planet's surface than our tropopause, the boundary between Earth's troposphere and stratosphere. That's a problem for astronomers trying to understand what's going on. They can't study the auroras from up close. The only way to see Uranus's auroras is from space, and we've only ever seen them from one direction, from the side. So although we can see the auroras, we don't know what they look like. We can't tell how high above the surface they appear or how big they are, and we don't know what they look like from Uranus's perspective. It's like trying to figure out what is going on at a parade by watching it on a live stream. You can see the floats passing by, but you can't tell what they look like or how big they are, or what the crowds are doing. And you definitely couldn't tell what the parade would look like if you were standing on the sidewalk. Luckily, we do have some tools to help us try to understand Uranus's auroras. For starters, we know the planet has rings. And in 1977, just months after Voyager 2 snapped the first beautiful views of these rings, astronomers noticed something crazy. A huge dark gap had opened up in one of the rings, a gap that could fit Earth's moon inside. The leading theory is that the gap was sheared off by the intense magnetic field lines that form near Uranus's magnetic poles. But other Uranus-gazing astronomers disagree. They argue that the gap was caused by plasma from Uranus's auroras slamming into the rings. Either way, the interaction between Uranus's auroras and its rings is definitely something to consider when trying to piece together what's happening. We also know that Uranus has at least a dozen known rings, but the majority of them are opaque and only a few miles wide. In other words, they're basically flat sheets rather than solid objects. Astronomers think that the best way to see Uranus's auroras is to look through one of these rings, because the auroras should be punching a hole in it. If we saw that, it would give us a great view of what's going on below the cloud tops, and help us learn more about the structure of the planet's atmosphere. Finally, we know that underneath the clouds, Uranus has a giant iron-nickel core. And here on Earth, we can use the planet's magnetic field to map out what's happening inside. See, magnetic fields are created by moving electric charges. Here on Earth, most of the charge carriers are really tiny and move really fast, like electrons whizzing around atoms. As the planet spins, these charges generate electric currents, and those currents generate magnetic field lines. Now, because Earth's magnetic field is a bit like a bar magnet, the magnetic field lines are pretty easy to map. But Uranus's magnetic field is shaped like an oval. And that means that mapping it is a whole lot harder. There are so many twists and turns that scientists haven't been able to trace the magnetic field lines all the way from the core to the surface. But eventually they hope to, because what's happening in the planet's core could hold the key to unraveling the mystery of its auroras. Uranus probably has a dynamo in its core, a swirling mass of liquid metal that generates a magnetic field. But it's hard to say for sure because the planet's atmosphere is so thick that it blocks our view of the core. And we can't hear what's going on either. Even though Uranus has an iron-nickel core, it's not metallic like we'd expect. It's actually a squishy ball of ice and rock. It's like trying to listen for a blacksmith hammering away in a wooden box. To solve this cosmic whodunit, we'll need more than circumstantial evidence. We need direct proof. We need to watch an aurora form and fade away. Luckily, we might get that chance soon. NASA's launching a mission called the Dark Energy Spectroscopic Instrument, or DESI, in 2022. To take a snapshot of every object in the night sky. By comparing what it sees now with what Hubble saw years ago, DESI will be able to spot changes in Uranus's auroras and rings. And if we can see how they change over time, maybe then we'll finally be able to solve the mystery of Uranus's auroras, once and for all. Thank you for watching this episode. which was brought to you by our incredible community of patrons. Y'all make it possible for us to bring mind-blowing space mysteries to the entire internet, and we appreciate the heck out of you for it. If you'd like to be involved helping us make this show, you can check out our support page,